To begin, let's go back to the problem we have been given and review the progress that we have made so far. We are given a planet's distance from the Sun and its velocity at perihelion, and our task is to find a formula for its orbit. We create a diagram and position the planet at an angle of azimuth equal to 0 degrees. The next few slides are a review. Feel free to pause the video anywhere if you need time to follow the reasoning. For comparison, we have previously introduced vref, the velocity of a planet in a circular orbit at a distance d0 from the Sun, and we recalled the formula for its magnitude shown here, which we derived from our consideration of circular orbits. We then defined Vmax in terms of vref, as shown here. And we found an expression for the specific angular momentum in terms of dp and delta, shown here on the left. Next, starting with the formula for r, the radius of the dv d theta circle in terms of h, we were able to derive a formula for r in terms of dp and delta. We then found an expression for the magnitude of Vmax in terms of delta and dp. And we discovered that the ratio of the magnitude of Vmax to r is 1 plus delta squared, which we simplified by introducing E prime. Based on our subsequent findings in part 5.4, which I will not review here, I will now be using E instead of E prime. Okay, so let's define our task. We're given Vmax for the planet at perihelion, and we are given its distance from the Sun, d, that is dp, and we want a formula such that for any given theta, we can derive d sub theta, the distance of the planet from the Sun at that point. There, of course, also will be a velocity involved, a new velocity somewhat less than Vmax, and there will also be a phi, an angle phi that is almost certainly different than 90 degrees. But we don't want those two variables in our equation. Remember, what we're looking for is d sub theta equals dp times 1 plus e over 1 plus e cosine theta, which would be the appropriate equation for an elliptical orbit. Now, the one key to our approach will be the specific angular momentum, which equals d sub theta times magnitude of v sub theta times sine phi. And we're going to use the fact that we've already found that h in this particular orbit equals the quantity 1 plus delta times the square root of g m dp. So the hope is that somehow we can combine these two equations and in the process somehow get rid of this and this. And I can give you a hint. The key to that task is to find an expression for phi. And that is what we will proceed to do right now. Our dv d theta circle. The center of the circle we mark with a dot and call it P1. we draw in Vmax, the tail of which lies at point P2. Now we draw in V theta, where theta could be any value between 0 and 2 pi. V theta touches the circle at point P3. We can draw a radius of length r from P1 to P3. Of course, it forms an angle theta with Vmax, the angle of azimuth. We now draw in a line segment from P3 to P4 on Vmax, so that P3, P4 is perpendicular to Vmax. Its length is r sine theta. The length of segment P1, P4 is r cosine theta. Recall that we have previously established that Vmax equals 1 plus e times r. Therefore, the length of segment P1, P2 is simply e times r. Vmax and V theta form an unknown angle, which we will call beta. Recall that we associate an angle alpha with any given velocity vector, where the reference direction is a horizontal ray to the right. It is clear from the diagram that alpha equals 90 plus beta. Phi, of course, equals alpha minus theta. Now we need to do some computations. Our goal is to evaluate sine phi. It equals the sine of alpha minus theta. There is a trigonometric identity for the sine of one angle minus another. In this case, sine alpha minus theta equals sine of alpha cosine theta minus cosine alpha sine theta. Now we use another trigonometric identity to evaluate sine alpha. By substitution first, it equals the sine of 90 degrees plus beta. This is identical in value to cosine beta. Let's move this term down to the next line. Now we go back and do a similar manipulation of cosine alpha. It equals cosine of 90 degrees plus beta, which in turn equals negative sine beta, which we also move down to the next line. We take cosine theta from above and move it down. We take sine theta from above and move it down. We bring down the minus sign and we see that we have subtraction of a negative number, so we change the two minus signs to a plus sign. So we wind up with this expression for sine phi. Now we evaluate cosine beta using the dv d theta circle. Clearly, it equals r cosine theta plus e times r divided by the absolute value of v theta. And we enter that term into the next line. We use analogous reasoning to evaluate sine beta. It equals r sine theta over the absolute value of v theta, and we insert that expression down into the next line. We insert cosine theta and sine theta into their respective positions in the new line. And we see that sine phi is equal to the expression on the right-hand side. Notice that we can factor out each of the three r's, and we can multiply what remains of the numerator of the first fraction by cosine theta, and we can multiply what remains of the numerator of the second fraction by sine theta, and we get this expression. Notice that we have a cosine squared theta and a sine squared theta, which we can add together to get 1, and we are left with an expression that is relatively simple. Let's move it into a fresh workspace. Remember as we go forward that r represents the radius of the dv d theta circle. We return now to our foundational equation and we rearrange it to give us this formula for d theta. We substitute for sine phi and we see that the two appearances of the absolute value of v theta will cancel each other out, so that we are left with this expression. Time now to use one of our key formulas to substitute for r. r equals gm over h. This gives us h squared over gm in the numerator and 1 plus e cosine theta in the denominator. But we can substitute for h as well. If h equals the quantity 1 plus delta times the square root of g times m times the distance at perihelion, dp, then h squared equals the square of the quantity 1 plus delta times g times m times d sub p. Now recall that earlier we made a choice to simplify an expression that involves delta, and in this case the quantity 1 plus delta squared is simply 1 plus e. So h squared equals the quantity 1 plus e times g times m times d sub p. Substituting for h squared, we get the exact formula for d theta that we were expecting to get if the orbit is an ellipse.